Okay, ECO311 Chapter 12, Autocorrelation. So again, same 4 topics: definition, consequences, detection, and remedies. So let's start with the definition. So the general definition of autocorrelation is that the error terms are correlated. And then the question is how strongly or how weakly are the error terms correlated. This is why we will do various detection tests later. And then autocorrelation is more likely to happen in time series data. Remember in the last chapter, heteroskedasticity is more likely to happen in cross-sectional data. And then again, just like the last chapter, we have 2 types, pure and impure. So pure autocorrelation means autocorrelation happens simply due to the poor data quality issues. But when it comes to impure autocorrelation, it means autocorrelation is caused by you as the culprit. So again, meaning you may have used the wrong functional form, you commit underfitting or overfitting. That relates to chapter 13, the last chapter. And in the next slide, why does autocorrelation happen? That's not prescribed, but you can have a look at these pages on the prescribed textbook, okay, just for your knowledge enrichment purposes. Consequences, okay. Most of them are bad consequences, actually. And in fact, these consequences are virtually the opposite of the consequences of imperfect multicollinearity from chapter 10. Okay, first one, I think this is the only consequence that is okay. The OLS estimators or the parameters remain linear and unbiased, but they are no longer efficient. In fact, the standard error of the parameters will become smaller. Remember, it is larger in chapter 10, multicollinearity, and then in chapter 11, heteroskedasticity, we said we don't know the direction of the bias. The standard error of the parameters could become larger or smaller. We don't know the direction. But for this chapter, autocorrelation, we know the direction. Definitely downward bias. Okay, and if standard error of the parameter will become smaller as a result of the presence of, let's say, significant autocorrelation, it will cause the confidence interval to become narrower. Again, go back to the equation on the confidence interval, the t-test, involving the t-distribution. Okay, and then if confidence, if the standard error of the parameter becomes smaller, it would also cause the computed t-stats to become exaggerated or inflated. Again, just to remind you, this is the formula for the computed t-stat. I use B3 slope parameter as an example. Okay, so this is the formula. So if the standard error of B3 hat or the standard error of the parameter becomes smaller as a result of the presence of significant autocorrelation, and this is the denominator term for the computed t-stat equation, wouldn't it cause the computed t-stat to become exaggerated or inflated? Okay, and then subsequently, it leads to unreliable hypothesis testing results because now it becomes much easier to reject the new hypothesis. Remember the graphical sketch from step 4 of the t-test. If your computed t-stat becomes inflated, exaggerated, or further away from 0, then it will become very much easier to lie in the rejection region. And then it also means it becomes much easier to reject the new hypothesis. Okay, so we can just briefly look at exercise 6, question 14. So I give you 2 regressions. The first one is fine, and then the second one is problematic with significant autocorrelation present. Okay, then I would ask you, based on the information from the 2 regressions, explain why you think significant autocorrelation is present, or maybe talk about the consequences. Okay, then you can talk about that. Oh, the parameters remain linear and unbiased. Don't you notice the constant B1 hat? Not much of a change. And then B2 hat, also not much of a change, hovering around 5.5. Okay, but do you notice the standard error of the parameter becomes smaller? Let's start with the first one. It used standard error of B1 hat, it used to be 5.55, but then in the second regression, with the presence of significant autocorrelation, don't you see the standard error of B1 hat becomes smaller, much smaller actually, dropping from 5.55 to 1.55. And then similarly, the standard error of B2 hat was 4.8 in the first regression. That is fine, but then in the second regression, with the presence of significant autocorrelation, standard error of B2 hat drops abruptly to 1.85. Okay, happy with that? If you really want to look at the full answers, please refer to the study guide. Okay. Okay. Then we can move on to talk about the detection. This is the unofficial method, graphical sketch. We usually plot residuals at time t versus residuals at time t-1. If you see this kind of strong positive relationship between the residuals from consecutive periods, that implies significant positive autocorrelation. And in this case, downward slope, it would imply significant negative autocorrelation. Remember from one of the assumptions of classical linear regression models, CLRM, from the earlier chapters from ECO311. One of the assumptions is that we want the error terms to have a normal distribution with a mean of 0. So in other words, we want the error terms to be sometimes negative, sometimes positive, positive, negative, positive, negative, so that on average, the error term would have a mean of 0 and with a normal distribution. Okay. Okay, detection, there are three methods. Let's start with the first method, the runs test. So I want you to look at this slide for 30 seconds. You will feel very confused actually. But once we do a numerical example, you would realize how easy it is. Okay, next slide. So just to remind you, for runs test, alpha is fixed at 5%. Definitely 5%. And for this test, luckily you don't need to use any statistical distribution table. Okay, confusing, eh? If you look at these two slides. So let's rather do a question actually. So okay, let's go to this one. So I will give you a table with the sign of the residuals. Okay, and then question 7, exercise 6. Okay, and then you need to answer the following question. N stands for sample size. 46, you clearly see 46. N1 stands for the number of positive residuals. So you have to count. Okay, these are the positive residuals. And then in total, N1, number of positive residuals, 24. Easy. And then the number of negative residuals, you also have to count. These are the negative residuals. And then in total, 22. Okay, N1 plus N2 must give you the total sample size. 24 plus 22 gives you 46. And now this is the important part, the number of runs. Okay, it actually means if we have a series of consecutive residuals with the same sign, then we count it as one run. Okay, so let's look at how many runs there are. This is the first run, all the negative residuals. First run, and then the second run from the 9th residual onwards, all the way up to the 29th residuals, they are all positive, a series of consecutive positive residuals. So this is my second run. Third run from number 30 all the way to 40, a series of negative residuals. So this is the third run. Okay, and this is the fourth run, a series of positive residuals. Finally, a series of negative residuals. This is the fifth run. So R, the number of runs, 5. And then actually from this table, you already suspect there could be significant autocorrelation, especially if you look at these long series of positive residuals. Remember, I previously said that we want residuals to have a random distribution, sometimes positive, sometimes negative, so that the mean of residuals would be 0 with a normal distribution. But this does not seem to be the case in this question 7. We suspect strong relationship between the error terms or residuals. Remember, we use residuals as proxy of error terms because we can only run sample regression function. Remember the time and budget constraint story. Okay, and then you need to work out these two equations. Okay, the equations is given to you in the formula sheet, so you don't need to memorize the equation. Okay, mean of run equals 2 times N1, 24 times N2, which is 22, divided by sample size, 46 plus 1. Then you get 23 point something. And then the next equation, the variance of runs. Again, the equation is given to you, then you just have to substitute the answers. Very straightforward, actually, except the equation is quite long, involving the brackets. Then you get 11 point something. And then you need to take the standard error, the square root. So standard deviation of the number of runs is square root of 11 point something. It gives you 3 point something. And then the next one, you need to work out this range. Again, the equation is given in the formula sheet. So the mean of run, 23 point something plus or minus 1.96 times the standard deviation of R. Then you get this range, 17 point something up to 30 point something. Okay, and now you need to remember the decision-making rule. If R, the number of runs, falls outside the above range, then it means significant autocorrelation is present in the regression. Okay, and I think this is the case because the number of runs R, which is 5, clearly falls outside this range. Then sorry, bad news, there is significant autocorrelation in the regression. Okay, so this is the runs test. Okay, and then there are a few more examples on the slides and in the in-class exercises, so I want you to do it on your own. Okay, then I would focus on the second test. Okay, Bruce-Godfrey test. So this is the story. I run the regression y as a function of x. It could be bivariate or multivariate regression. It doesn't really matter, but I think the textbook would, from the textbook, the focus is on bivariate regression, and then we extract the residuals, and then we run a second regression, residual explained by x and all the lag residuals up to that period t minus p. Okay, and then we calculate n minus p times r squared, but you must use the correct r squared. It comes from the auxiliary regression. And then you look for the chi-square statistics. Degrees of freedom stands for p, the total number of lag residuals in this regression. And if n minus p times r squared is greater than chi-square statistic, then sorry, bad news, there is significant autocorrelation. Then it actually means residuals at time t is strongly correlated with residuals in the previous period, the lag periods. Okay, you notice a little bit of similarity between these two steps of the Bruce-Godfrey test with the, I think it is the Y test from heteroskedasticity chapter. Okay, so we can do one question. In-class exercise 11. So this is my original regression. I will give you the R square to confuse you, although we won't use this R square. Then I extract the residuals, then I run the auxiliary regression, residuals explained by X, residual lag by 1 period, 2 periods, all the way to 8 periods. And this is the R square of the auxiliary regression which you have to use. And now the 5-step procedure, null hypothesis, insignificant autocorrelation. Alternative hypothesis, significant autocorrelation. So the aim of the Bruce-Godfrey test is we do not want to reject the null hypothesis. Okay, step 2, n minus p, so 50. I must give you the sample size. Minus p, 8 lag residuals in total in the auxiliary regression. So 50 minus 8 brackets times the R square. You must substitute the right R square from the auxiliary regression. Then you have 39 point something. Chi-square statistic, degrees of freedom is your total number of lag residuals in the auxiliary regression, so 8. Alpha is given 5%. So if you look at the chi-square table, 5%, 8, then you have 15.507. Okay. Then bad news, since n minus p times r squared, which is 39 point something, is greater than chi-square statistics, which is 15 point something. So sadly, null hypothesis is rejected. So the conclusion is quite sad, so that there is significant autocorrelation in the original regression. Actually, if you find very high R square in the auxiliary regression, it already implies autocorrelation is quite significant, because this R square actually means residuals at time t is strongly correlated with residuals in the previous periods. Then that implies a strong relationship of the residuals or the error terms. Okay, and then for the third detection method, the Durban-Watson d-test, you are going to learn to use the d-table, Durban-Watson d-table for the first time, and there are two tables, one for alpha at 5% and the other one for 1%.